Hello, in this video I solved the following problem. Probability theory. The topic is multivariate normal distribution. The random variables x sub 1 and x sub 2 are independent and n0 and 1 distributed. Set y sub 1 equals to x sub 1 squared minus x sub 2 squared all over the square root of x sub 1 squared plus x sub 2 squared, and y sub 2 equals to 2 times x1 times x2 all over the square root of x sub 1 squared plus x sub 2 squared. Show that y1 and y2 are independent, n0 and 1 distributed random variables. This problem is problem 3 on page 140 in the following book, an intermediate course in probability, second edition, Springer 2009 by Alan Guth. Pause the video at this point and give it a try. Okay, first let me explain what is my general strategy to tackle the problem. If you are studying this course, you are experienced enough in mathematics that somehow by seeing this combination in a problem, it might remind you about the switching to the polar coordinates. Having that experience in our toolbox, I will also try to solve this problem using the polar transformation of the coordinates. Here by coordinates I mean the random variables x sub 1 and x sub 2. So my strategy will be this. Because they have given us that x sub 1 and x sub 2 are independent random variables, and they have given us that both of them are normally distributed with the standard normal distribution, what I can find from that piece of information, it would be easy to write the joint probability distribution for these two random variables. Then what I will do, I will introduce the polar coordinates, polar random variables, if you want to say, capital R and capital theta. And then using the transformation theorem, I will be able to write the probability to find the probability, the joint probability distribution for these new random variables R and theta as a function, let us say, of R and theta. And then I will apply the polar transformation here and there, and I will see that y sub 1 and y sub 2 relate themselves to these random variables R and theta in a very simple and nice way. Then what I will do, I will use the transformation theorem again to go and finally find the joint probability distribution for new random variables y sub 1 and y sub 2. And then I will see that, okay, this joint probability distribution turns out to be the product of two standard normal distributions. So this means that y sub 1 and y sub 2 are not only independent of one another, but both of them are also distributed normally with the standard normal distribution. So this is the general strategy. But here there will be some delicate points, because you will see that the transformation taking me from here to here is not one-to-one, so we have to use the modified version of the transformation theorem. But this is the general scheme that I'm going to follow. Okay, so let us now go to the solution. x1 is normal, this has normal distribution, so this means that if capital x1 is 1 over square root of 2 pi e to the power of minus x1 squared over 2 for x a real number, any real number. And I also know that x sub 2 has the same distribution, so this means that f sub x2 of x2 is 1 over square root of 2 pi exponential of minus x squared x sub 2 squared over 2. But I also know that x1 and x2 are independent according to the problem, so then this means that the joint probability distribution is just simply the product of these probability distributions. So this means that I multiply this function by that function, and then I have this factor which is multiplied by the same factor will give me 1 over 2 pi, and I add the exponents. So I would write e minus x1 squared plus x sub 2 squared divided by 2, and this means x1 is any real number, x2 is any real number, so this means that x sub 1, x sub 2 belongs to r squared. So it means there are no limitations for the values of x1 and x2. Okay, so let me put this in a box. I have this function now here. But now what I want to do, I want to do the first step. So I want to switch to polar coordinates. So what I will introduce is, I will introduce that x sub 1 is r cosine theta. So here capital R and capital theta are new random variables involved in the problem. And then x sub 2 is r cosine theta. So I'm introducing these variables. And then of course you know that for standard polar transformation r is positive, and I keep theta within this interval to respect the one-to-oneness, injectivity of the transformation, which is indeed needed for the transformation theorem. Okay, and then, so remember here, x1 and x2 are the old variables, r and theta are the new variables. So the first thing that I have to do, I have to calculate the Jacobian of the old variables in terms of new variables. So in other words, I want to calculate this. And if you don't mind, let me just switch to little letters. So eventually I have to do that. So this becomes the Jacobian of x1 and x2 with respect to r and theta. So the Jacobian is the determinant, the partial derivative of x1 with respect to r written here, partial derivative of x1 with respect to theta written here. So I refer to this one and I do the calculations. Partial derivative of x1 with respect to r just becomes simply cosine theta. The other one becomes minus r sine theta. And now partial derivative of x2 with respect to r is sine theta, and the other one will be r sine theta. Oops, I made a mistake here. This is not, this is sine theta, sorry. Okay, so this becomes, yeah, that's correct. And then this one becomes r cosine theta. That's correct. Okay, and then I calculate this determinant. So this becomes the product of these minus the product of these. So this becomes r cosine theta squared plus r sine theta squared, which is nothing except r. Okay, so now using the transformation theorem and considering that this transformation here is actually one-to-one, yes, this transformation on this domain is exactly one-to-one. This is a transformation from this domain to this domain in a one-to-one way. So what we should do, we just write f of the new variables r and theta are the old ones, so x sub 1 and x sub 2. Here I have to write x1 and x2, but I want to write them in terms of r and theta, that I have them here. So this becomes simply r cosine theta and r sine theta, but multiplied by the absolute value of the Jacobian. But Jacobian is r, and r is positive, so I don't need absolute value, I just write r here. But here I have to respect that r is positive and theta is between 0 and 2 pi. Okay, but that's very simple. This is the function f sub x1 and sub x2. The only thing I have to do, I have to go to this formula, replace x sub 1 with r cosine theta and replace x sub 2 with r sine theta. Remember about this r. So if you don't mind, let me multiply this r by this factor first. So this becomes r over 2 pi. So let me write it in this way. So this means that f capital R capital theta calculated at r and theta is equal to r over 2 pi and then e to the power of minus r squared over 2. And the reason is clear, yes? Because if you calculate this combination for this, it becomes r squared. Okay, so I was also able to find this. And of course, let me also to emphasize, write the support. R is positive and theta is between 0 and 2 pi. Okay? Okay, now let me, I want to, now, so I started here, I am now here, and I want to go here. So this means that I need to know how y sub 1 and y sub 2 relate themselves to the polar coordinates, polar random variables r and theta. So that's simple. So instead of x sub 1, I put this, and instead of x sub 2, I put this, and then do some calculations. But the calculations are extremely simple. For example, here, y sub 1 is equal to x sub 1 squared becomes r squared cosine theta squared minus r squared sine theta squared divided by square root of the first one squared, yes, plus the second one squared. Okay, but in the numerator I factor r squared, and then it becomes cosine theta squared minus sine theta squared, and that's a famous formula. It's cosine of the double angle. And in the denominator, if I factor r squared, then I will have cosine plus sine, cosine squared plus sine squared, which is 1, so it becomes simply r. Yes, and that r and that r are cancelled. So finally, I will have y1 equals to r cosine 2 theta. Okay. And then if I do similar calculation for y2, so the denominator is still r, that's the same denominator as before, but when I multiply them, so what happens, this r and this r will be multiplied, so it gives me r squared, and then I will have 2 cosine theta sine theta, which is a famous formula for sine 2 theta. And 1 r in the numerator and 1 r in the cancels, the r in the denominator, so finally we similarly we have y sub 2 is equal to r sine 2 theta. Okay? Okay. But now I want to go from r and theta variables, and probably joint distribution for capital R and theta, which I have it here, to some new variables y sub 1 and y sub 2, which relate themselves to r and theta through this relation. So these are also very similar to the polar coordinates, but the only difference is that instead of usual angle theta, we have 2 times theta. And now it means that this transformation is not a one-to-one transformation from this support to this support. It's a 2-to-1 transformation. Yes, so if I restrict theta between 0 and pi, because of this factor of 2, all r squared will be covered. But then if I go from pi to 2 pi, I will cover every pair of real numbers once more. So according to the modified version of the transformation theorem, I have to restrict the support to the sub-supports, if you like, so that this transformation on each sub-support is one-to-one, and then add them up. So that is the idea. Okay? So let me write it here. So for example, if I want to do it, it becomes like this. So I would write f of y1 and y2, the new variables, let us say in terms of little y sub 1, little y sub 2, is equal to f, r, and theta and then I have to express r and theta in terms of y1 and y2. But in this case, it is a little bit subtle if I want to do that. So I can pretend that I have done it, and I can say that, okay, I write it as r, but I know that I have to write it in terms of y sub 1 and y sub 2. Of course, I will suppress this y sub 1 and y sub 2, but for your understanding, I will write it down here. And theta should be expressed in terms of y sub 1 and y sub 2. And then I have to multiply it by the Jacobian of the old variables, in this case r and theta, with respect to the new variables y sub 1 and y sub 2. But of course, I have to take the absolute value. But this is not the whole story, because as I told you, I have restricted my support to this support that theta is between 0 and pi to make this transformation injective, one-to-one. And I have to consider the other scenario that r is positive, but theta is between pi and 2 pi, which will cover the whole set of r squared once more. It will be something similar to this, so I have to add these together. Okay. But when I do the calculations, you will see that this combination will not depend on theta. So if I want to add one more, because this calculation shows that it is independent of theta, so this means that and the value of theta is the only thing that changes between the first term and the second term, I can just simply multiply it by 2. So that is extremely important to realize that. So because of that explanation, let me put a 2 here. So this 2 means that I am adding these two, one on sub-support, in which theta is between 0 and pi, and the other one another subsupport in which theta is between pi and 2 pi. But the calculation will reveal that these terms are independent of theta, so both of them will be equal. So that's why instead of adding them, I just multiply one of them by 2. Okay. So the other thing that you need to be careful here, in order to calculate this Jacobian, you need r and theta be expressed in terms of y sub 1 and y sub 2, which becomes a little bit messy if I want to do that, but there is a theorem that this one is the reciprocal of the other way around. So what I will do, I will continue and write it 2f r and theta at r y sub 1 and y sub 2, and theta y sub 1 and y sub 2. So be careful. In principle, I have to write r in terms of r1 and r2 because that's a delicate, I mean, it takes time. It's possible, and then I have to be very careful about how I do this inverse transformation, and you will see that this will not play any role. But pretend that we have done that calculations, okay? So then it becomes multiplied by 1 over the Jacobian in the other way. So it will be the Jacobian of y1 and y2 with respect to r and theta. Okay? So let us continue now. So here, this is my function. So I put these expressions inside this function. Okay, so this becomes 2. And then I have r, which in this case is r of y1 and y2. But no, so keep it in mind, but don't write it up, not to mess up the situation. Times 2 pi, and then multiplied by e to the power of only r squared, yes, minus r squared over 2 multiplied by 1 over, now let us calculate the Jacobian. So partial derivative of y1 with respect to r is cosine 2 theta. The other one will be minus 2r sine 2 theta if I differentiate it with respect to theta. and then for y2 it becomes sine 2 theta, and then plus 2r cosine 2 theta. Yes, and then of course I have to have absolute value. So if I continue, I simplify the 2, so it becomes r over pi e to the power of minus r squared over 2. And then if I calculate that determinant, this multiplied by that minus this multiplied by that, it gives me just simply 2r. And because r is positive, I don't need absolute value, so it becomes 1 over 2r. And now what happens? R and R are cancelled, so it becomes 1 over 2 pi e to the power of minus r squared over 2. But be careful. This is expressed in r. I have to express this in terms of my new variables y1 and y2, but that is very simple to see that y1 squared plus y2 squared is nothing except r squared. So instead of r squared, I can put that expression, and you see that this result is independent of theta, which justifies what I told you shortly. So this becomes 1 over 2 pi, and then I have exponential of minus y1 squared plus y2 squared divided by 2. Okay, so there's no place here, so let me go to the next page, but remember this result. So what we have done, we have shown that this expression is equal to that, yes? Okay, so this is the result we got, but this is very simple to see that you can write this again as the product of 1 over square root of 2 pi exponential minus y squared to the power of 2 divided by 2 multiplied by a similar expression. Okay, so I was able to show that the joint probability distribution for y sub 1 and y sub 2 can be written as a product of a function which is a function of y sub 1 only and a function of y sub 2 only. So this already tells me that this y1 and y2 are independent, and of course I forgot to write here that y1 and y2 belongs to r squared, so it covers the whole r squared. So this means that first of all, they are independent, and each one of them is the probability distribution of each one of them. So if you really want to prove that, you can integrate over the other one. Yeah, for example, if you want to calculate this, in principle, if you want to calculate this, you just integrate of that function over the other variable and then go from minus infinity to infinity. It's very simple that you will get this function back, yes. And these are standard theorems, so okay, you don't need to do these things because you know that this function is the product of two functions. One function is a function of y1 only and the other one is a function of y2 only. So y sub 1 and y sub 2 are independent, and these ones are individual marginal distributions. So it means that yes, y1 and y2 are both standard normally distributed and they are independent. Okay, I hope that this video was useful for you. Until the next video, be safe and goodbye. Thank you.